Okay, so big idea for this unit is when a force between two objects acts for some time, it creates an impulse, right? The force between two objects that acts for some time. This is a nice way of saying impulse. We spent a whole bunch of time at the beginning of the unit on impulse. And the reason we did is because that impulse causes a change in momentum, right? That's the big idea for this unit. It's actually so important that I put it up on the top, the change in momentum and impulse, and it's right in the center, right? Applying a force for a certain amount of time causes an object to change its momentum. In fact, it causes a change in momentum for both objects if two objects interact, and that leads to conservation of momentum. For your test on Monday, here is what I am picturing. Trying to make it so you can see all the things. There we go. For your test on Monday, what I'm picturing is I'm going to ask you about the same amount of questions as last time. So a formative that's going to have 4 sections, probably about 8 or 10 points per section, something along those lines. And those 4 sections are going to test different things on this board. Okay. So what are they going to test? Well, they kind of go in order of this unit. We started the unit with impulse. And there were a few different ways you can calculate impulse. So let's say if you were studying for the test, or you're making yourself a study sheet for the test that's got all your info in one place, I would say thing number 1 is we spent about 40 minutes in class watching videos about like car crashes and impulse and how we keep people safe. During that, we calculated force times time as one way of calculating impulse, and how to use area under the curve to calculate impulse when your force isn't constant. So I may expect at least one problem, like 1/4, 1/4 of your test, at least 1/4 of your test is going to be about impulse and collisions. This is the part where we were doing things like, we looked at like older unsafe cars versus newer safe cars. Back in the day, they made all cars out of stainless steel, very tough, very inflexible. And so when a car crashed, the car itself would experience a very large force over a short period of time. If I were to analyze the impulse of this, I can see people come in from the weight room. Okay. If I were to analyze this, I would want to use area under a curve, not force times time. Force times time works if I have a constant force, but this force like gets bigger and smaller. So I want to use area under a curve. This shows an unsafe collision because it shows a very large force acting for a small amount of time. And they talked about how modern cars make collisions safer. Modern cars make collisions safer because what they do is they take the same impulse and they spread it out over a longer time. Now, a bunch of you guys got this wrong on the review on Monday. How do I make it the same impulse, but different forces? Well, I've got to keep the area under the curve the same. So what I'm going to do is I'm going to double the time. Right? I'm spreading this impulse out over a longer period of time, and that's going to cut in half the force. This means small force over a large time. Blue is the safer collision for my person. Okay? And the thing that these two graphs have in common with each other is this is the same impulse. Imagine I'm crashing 2 cars, so they have the same mass, the same initial velocity. They both go to rest during the crash. So they have the same impulse, same momentum, same area under the curve, but different outcomes for my people. So I would think at least one question or 1/4 or so of your test, 1/4 of your test on impulse and collisions, how to calculate force times time, how to calculate area under a curve, how force and time are inversely related, taking the same collision and making it safer by making a long time with a small force. Inverses. If you are stuck and you're like, I don't recognize any of this, where you can review this, you can review this all on homework 3.1. 3.1 has all the practice problems for that. Okay. All right. The last way to calculate impulse, though, was important enough that it's the key to this unit. It's the main sentence up here and the main sentence down here. That probably indicates that it's important enough for its own problem. This is called the impulse momentum theorem. The impulse momentum theorem is important enough to be its own problem. So if you imagine section 1 is on impulse and collisions, then section 2 is going to be down here on impulse momentum theorem. Now, in case you don't remember this, how about I put it on a different board so we got some space here. Okay. Impulse momentum theorem. This is the one that says if I apply a force in time, if I apply an impulse, right? I push on an object for some time. That's going to cause an object to change its velocity. And if it changes its velocity, it changes its momentum. So applying a force for some period of time changes an object's momentum. That's called impulse momentum theorem. And if you were stuck on number 8 on the review, the one where like, if the impulse of the tennis ball equal to the change in momentum of the tennis ball, that's what it was getting at, but in words instead of symbols. So let's work on a problem like this. You'll be able to tell an impulse momentum apart from a conservation of momentum apart because impulse is one object at a time. So this might be something like a tennis ball, right? A tennis ball going at 10 meters per second. I'm going to make it a really heavy tennis ball so I have easy numbers to work with. Hits a wall and bounces backward. And now is going 8 meters per second in the opposite direction. Well, because the momentum changes, there must be an impulse that acts upon it. And if you wanted to, you could write this as impulse J. Okay. So how do I find impulse? I'm going to get the mass and velocity before and the mass and velocity after. And then I'm going to subtract them. This is not adding them. It's not conservation. There's no setting equal or anything here. When I'm dealing with one object, conservation of momentum doesn't apply. So this thing starts off, and there are 5 Newton seconds of momentum to start. Positive because it's going to the right. Whereas there's 4 Newton seconds at the end, but it's negative because it's going to the left. I'm not going to set these equal to each other because they're clearly not equal to each other, like 5 doesn't equal 4. But how do I get the impulse from here? Impulse was caused or causes the change in momentum. So I'm going to take the final momentum, that's 4. And the initial momentum, that's 5. And I get negative 9 Newton seconds. The picture you most often see with impulse momentum theorem, you most often see a bar graph. And the reason you most often see a bar graph is because it helps me picture the impulse. The impulse causes the change. So if it starts at 5 and ends at negative 4, the impulse caused it to decrease. And it decreased by 9 units. That must mean some force pushed on this ball to the left, causing it to change momentum from positive to negative. The other way you might see this is you might see this in a velocity versus time graph. In a velocity versus time graph, You actually don't have to deal with the mass at all. This goes from 10 meters per second to start and ends up at -8 meters per second at the bottom. So then I would simply connect the dots in between. So your graph might look like two funky trapezoid things. That number on the bottom is a -8. Okay. So if you're stuck on impulse momentum theorem and you're like, I need to review that, go try homework 3.2. So to recap where we've got so far, on your test, expect 4 sections. One is going to be this, impulse in collisions. It follows along with homework 3.1. Part 2 is going to be something like impulse momentum. It is going to follow along with homework 3.2. Then, don't know if you remember, we did Newton's third law. We did a pivot lab, and we played at quizzes. So I would expect maybe that is the next thing. Newton's third law. In Newton's third law, you should be able to do a bunch of different little things, like identify force pairs. So how about we do a gravity one, right? So how about a ball is pulled down by the earth? So we know that a ball is pulled down by earth. But Newton's third law says that forces are interactions between two objects. So I'm going to identify my objects. Ball, earth. They're interacting with each other. That must mean if the ball is pulled down by the earth, that means the earth is pulled up by the ball. And that might sound weird, but it's actually not. You are currently pulling the earth up right now. We just don't notice it. Up by ball. We just don't notice it because there's a huge difference in masses. So let's talk about Newton's third law. You should be able to identify, these are called force pairs. So the ball pulled down by earth, earth pulled up by ball. I know those are a force pair because it's the same two objects in both statements, and they switch direction. Ball is pulled down, earth is pulled up. Cool, so two objects, they switch directions. Equal magnitude. Equal magnitude means these are the same number of force. So maybe the ball has a weight of 10 newtons. Technically that's negative because it's going down. But gravity, that must be also pulling up the earth at positive 10 newtons. The reason we don't notice this is even though they experience the same force, well, the ball is much less massive. So that means if it has a little tiny mass, it has a big acceleration. Whereas the Earth is a really enormously, incredible, big mass, so functionally no acceleration. So even though they experience equal magnitude forces, they accelerate differently because they're different masses. Okay? A thing in Newton's third law that people can kind of get confused on sometimes is they're like, wait a second, shouldn't the -10 cancel the +10? No, it does not. The reason these don't cancel each other is they act on different objects. There's only one, imagine this goes away, right? There's only one force on the ball. It's not being canceled by anything because there's no other forces acting on it. So these force pairs don't cancel each other. Force pairs don't cancel. And they don't cancel because they act on different objects. Right? So when we originally did Newton's third law, I repeatedly gave the example of punching someone in the face. The reason that doesn't cancel out and I both injure my hand and I also injure their face is because my hand and their face are different objects. So I don't hit them and nothing happens. I hit them and two forces occur, a force that hurts my hand and a force that hurts their face. Equal and opposite. So I'm expecting something on Newton's third law. If you were stuck on Newton's third law and you're like, I just need some extra practice, go practice this with the Newton's third law quizzes that's posted to the classroom. So I'm telling you like all the stuff in this unit, right? And where to practice it. So homework 3.1, 3.2, the quizzes, and 3.3, which you just worked on. So to close out our review, the last fourth, the last quarter of your test is going to be conservation of momentum, right? What we were just working on. That's why I wanted you to start it on Wednesday, guys. So you didn't have to like learn it all and review it all in the same day. So conservation of momentum then. This is going to be your last quarter of the test. It won't necessarily be in this order and it won't necessarily be as clear cut. Like maybe I ask a question that starts as conservation of momentum and ends with asking you about force pairs, but that's okay. Let me change markers so that you can actually see what I'm writing on this board. That's not helpful at all. Last thing, conservation of momentum. If you get stuck on this, check homework 3.3. And the idea with conservation of momentum is that momentum is transferred from one object to another object. So I'm going to do a really easy one here. Let's say I've got a 2 kilogram triangle and it's going 10 meters per second and it hits a stationary medicine ball, which is very massive. That's like 16 pounds. So it's not like the worst medicine ball ever. But afterwards, they bounce off each other. All right, the triangle bounces backwards. Let's make this -6. Nice, easy numbers to work with. And I don't know how fast the ball is going. Conservation of momentum means the momentum on the left has to equal the total momentum on the right. So I'm going to start by drawing my picture. Then I'm going to calculate mass and velocity. I'm going to calculate momentum for each object. So this would be 2 times 10 plus 8 times 0. This is 2 times -6 plus 8 times, I don't know. That means I have 20 Newton seconds of momentum to start. That's how much momentum my triangle has. And I'm going to deal just with the triangle in this picture for a second. The triangle has 20 Newton seconds of momentum. Afterwards, though, the triangle has -12 Newton seconds of momentum. The triangle loses momentum. Well, that must mean that the ball picked up momentum, right? In this case, the triangle loses 32 Newton seconds of momentum. That must mean the ball picks up 32 Newton seconds of momentum, and I can use the ball's final momentum to find its velocity. Okay, so I'm going to add 12 to the other side. That means 32 equals 8F for a final velocity of 4. The ball picks up momentum because the triangle lost momentum. A thing that people mess up on this problem with is they'll look at it and be like, oh, the momentum of the triangle is conserved. But that's not true. The triangle lost momentum. right? Triangle loses momentum. Right? People would say things like the ball has conservation of momentum. And that's not true either. The ball gains momentum. It goes from 0 to 32. The ball gains momentum. Conservation of momentum is that the two of them together have conserved momentum. You can only conserve if you have at least two things interacting with each other. I can't have conservation of money if I just like throw my money up into the air. I need to give it to somebody. It needs to be orderly. So conservation of momentum, be able to solve for a final velocity, be able to depict it with bar graphs. Ooh, be able to depict it with velocity versus time graphs. Let's draw one of those out real quick. The velocity versus time graph for this would be that the triangle loses velocity. The triangle goes from a velocity of 10 down to a velocity of -6. And then I connect the dots. So orange is going to be the triangle. On the other hand, the ball starts at 0 and ends with a velocity of 4. And then connect the dots. There's that like trapezoid shape again. So that's what I'm thinking for your test next week. What you're gonna wanna do before that is take all of these like different ideas and put them into some sort of logical place that's easy to refer to. So what, huh?
Can you go back to that graph you made?
Yes, I can. Here, wait.
All right, I see it.
Cool. Just like move to the side. Oh, and that's a velocity versus time graph. There we go. All right. So what I'm going to have us do for the next 10 or so minutes is I want you to start making one sheet for yourself that takes all your notes and all these ideas and puts them together in just one place. And I do have a thing that's going to help you with that. There we go. Better camera. The thing that I have that's going to help you with this is that I'm going to give you something to start with. So something to start with. In Classroom and Drive, or actually just in Classroom and Slides, I put a link to this document that's called Units 1 through 3, Equations and Objectives. That way, even if like you missed notes or you missed days, at least you know what should be on your sheet. So what should be on your sheet? It should have at least these 4 equations, the stuff from Unit 3, but also the Unit 3 objectives. So what I mean by objectives is these are the things that you're supposed to be able to do by the end of the unit. They're like kind of my end teaching goals. It's what I want you to be able to learn from me in like the 2 weeks that we did this. And what I did when I was writing this test was I literally took every one of those standards. I put them in a document. I switched their order around and I wrote problems around them. So I know that somewhere in the test, I'm going to ask you to draw a force versus time graph for a safer collision. I know somewhere in the test, I'm going to ask you to calculate the velocity using conservation of momentum. I know somewhere in the test, I'm going to ask you to identify a force pair. So what you can do is use this objective list as a checklist. Be like, either I understand this, check, or I wrote it on my note sheet, check. So even if I don't understand it now, at least I've got it to refer back to later. So what I'm going to do is I'm going to go send you off with random breakout rooms this time And what I want your group to figure out is what you're going to put down on your sheet. Someone in a previous class was like, oh, do I need to put stuff from previous units? No, I put the previous unit equations there as a reference in case like you do get an area under the curve or you do get something having to do with acceleration, but you're probably not going to need those. They're just there for reference. So focus on unit 3. Focus on these equations and objectives, how you would get those all onto one sheet of paper. Someone asked, does it have to be paper? I'm gonna go with no. However, what I will say is I did have at least one person make like notes for themselves for the last test, but they left it on their iPad. So then they kept switching back and forth between the formative and their notes, and they kept like sidetracking themselves. And it did not work out well. The reason I suggest a separate piece of paper or to put it up on a separate monitor is so that you can have like your test on one device and then your work goes somewhere else. So let's give you guys some time to work and figure out what you're going to put in these things. I've got breakout rooms being randomly created right now. Good luck. I will pop into each breakout room to see how you're doing.